Hello everyone. In this video, we're going to learn how to write the shorthand electron configuration or condensed electron configuration of elements. Now let's take helium as an example. Helium has an electronic structure of 1s2. Now if we were to write boron, for example, we would write 1s2, 2s2, then 2p1. Now, instead of writing 1s2, 2s2, 2p1, we can summarize this by writing it as He, 2s2, 2p1. It would also mean boron as well. If we're trying to see from the periodic table, it's like helium, then 2s2, 2p1. Neon has 10 electrons, and it would make neon 1s2, 2s2, 2p6. If we were to write the electronic configuration of magnesium 12, magnesium has 2 extra electrons than neon 10. So until here would be 10 electrons. Then you simply add in 3s2. Now, in this case, it's a similar thing as well. You don't have to write 1s2, 2s2, 2p6. Instead, you can simply write neon and 3s2 here. Argon has 18 electrons. 3s2 and 3p6. If we were going to write, let's say, the electron configuration of titanium, which has 22 electrons. So until here, we know that there's going to be 18 electrons. So after that, we're only left with 4s2 and 3d2. In this case, it's the same thing as well. You don't have to write the entire thing. Write down the noble gas on the period that is above it, then just write whatever is in front of it. This would make it AR, 4s2, 3d2 here. Let's say you're asked to write down the electron configuration of an atom with a ridiculous amount of electrons. Let's say cesium 55. How do you write down the electron configuration of it? Cesium is here. So we're going to go to one period above it and to the noble gas here. So the shorthand notation is going to look like xenon 6s1. Then you have the electron configuration of cesium. We learned about Aufbau's principle and Hahn rule to fill in electron configuration. But there are two elements in A levels which are exceptions to that rule, and we're going to take a look at it. Chromium has 24 electrons, and writing down the electron configuration, it would look like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Until now, how many electrons do we have? We have 20 electrons already, so we only need to fill 4 electrons in 3d4. Now, if we use the atomic orbitals to fill it, it's going to look something like this. 1, 2. 1, 2, 3, 4, 5, 6. 1, 2. Then for 3d4, 1, 2, 3, 4. Now, the exception to writing the electron configuration for chromium that you need to know is that we have a full subshell here and we don't have anything here. So the rule here is that the half-filled or completely filled orbitals are more stable than those which doesn't have any electrons. Now we have atomic orbitals here that doesn't have any electron, and that's why one electron from 4s is gonna have to go over there to make it two half-filled orbitals. Take a look at this. And now we have two half-filled atomic orbitals, which is more stable than the ones that we had. That's why instead of writing 4s2 3d4, this is wrong. The correct way to write this would be 4s1 and 3d5. The electron configuration of copper would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. How many electrons do we have until now? We have 20 electrons already, so we only need to fill in 9 electrons in 3d9. And let's fill it up in the atomic orbitals. It's going to look something like for 1s and 2s, for 2p6, 1, 2, 3, 4, 5, 6. 3s, 1, 2, 3, 4, 5, 6. For 4s, for 3d is 9 electrons, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. When you take a look at this, we have a full atomic orbital here, but the 3D atomic orbital is neither half-filled or fully filled. So the more energetically stable electronic structure for this would be for this one electron from 4s to go to the 3D atomic orbital and make it a full filled 3D atomic orbital here. Now we have the correct version. So instead of 4s2 3d9, the correct structure would be 4s1 3d10. In summary, the wrong version to write chromium would be 4s2 and 3d4. It should be 4s1 and 3d5. And in the exam, if you are asked with the question, why is it going to have 4s1 and 3d5 instead of 4s2 and 3d4, you can simply answer it by saying that 4s1 3d5 atomic orbitals are more energetically stable than 4s2 3d4 because 4s1 3d5 atomic orbitals are both half-filled subshells. For copper, the wrong way to write this would be writing 4s2 3d9 at the very end. The right way to write this is 4s1 and 3d10. So in the exam, expect questions like why is it written as 4s1 3d10 instead of 4s2 3d9? Your answer would be the same as the chromium example. Now, let's learn how to write the electron configuration of ions. So sodium, which has 11 electrons, will have an electronic structure that looks like this. Sodium, when it were to become a positive sodium ion, it's going to have to lose one electron. That's why sodium ion, we're simply going to just remove one electron here. The electronic structure of chlorine atom looks like this. What would the electronic configuration of chloride ion look like? Which is Cl17 minus. So in order for chlorine to become a negative ion, it must gain an electron. So we're simply going to add one electron. So instead of being 3p5, this is going to be 3p6. The electronic configuration of ions, when it involves the d block elements, it becomes a little bit more complicated, but let's take a look at it. Titanium, which has 22 electrons, the electron configuration will look something like this. So let's try to fill up our atomic orbitals here. 1s2, 2s2, 2p6 would be 1, 2, 3, 4, 5, 6. Then 3s2, 1, 2. 3p6 would be 1, 2, 3, 4, 5, 6. 3p6. And this is where you need to pay attention. 4s atomic orbital has lower energy than 3d atomic orbital. That's why we're going to fill in 4s2 first. Then only after that, we're going to fill in the 3d atomic orbital. It would make sense to you that since we fill in the 4s atomic orbital here first before the 3d atomic orbital, when it is to lose an electron to become a positive ion, the electron is going to leave the 4s atomic orbital first. That's why the electronic configuration of titanium ion would be 4s1, 3d2, because we'll take away an electron from here first. Now, if it were to become a 2 plus ion, we're going to have to lose one more electron, and that one more electron is gonna come out of 4s as well. But instead this time, you completely remove the 4s1, and this will be the electronic configuration of titanium ion. Let's take a look at chromium atom when it becomes a chromium 2 plus ion and a chromium 3 plus ion. We've learned about this exception here a few minutes ago, so let's fill in the electrons in their respective atomic orbitals. 1s2, 1, 2, 2s2, 1, 2, 2p6, 1, 2, 3, 4, 5, 6, 3s2, 1, 2, 3p6, 1, 2, 3, 4, 5, 6. Now, 4s1 and then 3d5. 1, 2, 3, 4, 5. Now, if chromium were to become a 2 plus ion, it's going to have to lose 2 electrons. The first electron is going to come out of the 4s atomic orbital, and the next electron is going to come out from the 3d atomic orbital. So I'm going to cross out one electron here and one electron here. That would make the electronic structure of Cr2 plus 2b, 3p6, and 3d4 here. If we were to have Cr3 plus ion, we are going to lose one more electron, and that electron is going to come out of the 3d atomic orbital. So this will become 3d3 here. Thank you for watching the video. I hope you learn a little bit better about writing down electron configurations. Leave a like or a comment down below if you find this helpful. Bye bye.